everyone, so this video is on transformations. There are a few different types of transformations. You should be pretty familiar with these, but in any sort of transformation, what you're doing is taking every point from an original object, transforming it in some way to get some new image. And what we do is you call the original object the pre-image and the new object the image. For example, if I took this rectangle and I slid it over or translated it to get a new rectangle, we would call this the pre-image because it's what I started with, and this is the image. The way we denote this is, let's say this was A, B, C, and D, those were the points. Then I would call the new image, so that's the pre-image, the image we denote with little apostrophes. And these apostrophes, you say it as prime. So what I mean by that is, you would call this A prime, B prime, C prime, and D prime. And then if you could actually keep compounding this. So like if I slid this one down and got a new image, I would call this A double prime, and B double prime, C double prime, D double prime, and you could just keep going from there. There are a few different types of transformations. This that I've been doing, where you slide or just move it, is called a translation. You could also have a reflection, which is you flip it across some axis, forming like a mirror image. You could rotate, so just twist it around a point. And then you have a dilation. Just like you might get your pupils dilated, dilation is a stretch or a shrink. These three I put in blue because these three are kind of similar. We call those three rigid transformations. Because these three don't change the size or shape of your object. A dilation is not going to change the shape, but it is going to change the size. It might get bigger or smaller. But with all three of these, the shape stays rigid. It doesn't move, it moves, but all the lengths and angles stay the same. Every single new image is congruent to the pre-image. So here's some examples of those. A translation is a slide. A reflection, you flip. Rotation is you rotate a certain angle around a center point. And dilation, you might change size. So again, for those three rigid transformations, the pre-image and the image are completely congruent. Remember, congruent just means like equal but with shapes. That means all the lengths are preserved, meaning the lengths from like AB is the same as the length from A prime to B prime. And the angles are preserved. So whatever angle A is, that's the same as angle A prime. Everything is congruent, everything is preserved. So let's do a few examples. Okay, so translations are pretty straightforward. If I want to translate it 2 units to the right, I'm literally like picking up this blue shape and shifting it 2 units to the right. It's helpful to me to sometimes do it 1 point at a time. So like if I move the point T 2 units to the right, I would land here. That's T prime, the image. If I move point E 2 points to the right, that's E prime. M would be M prime right here if I move it 2 to the right, and move I 2 to the right, there's I prime. And I'm also moving every single one of these other points too. So like I'd pick up this point and move it 2 units to the right, and I'd pick up this point and move it 2 units to the right. But basically, if we just connect the dots at this point, it shouldn't be that hard to do. And there I have my image. That's the pre-image, this is the image. There we go. Translated it 2 units to the right. What if I want to go 2 right and 1 up? Same thing, but just go 2 right and 1 up. Now that's T prime. to right, up 1, to right, up 1, to right, up 1, and again, I'll connect the dots. All the points got shifted, but it's pretty easy for me to draw the rest of them now. So that got slid right and up. All right, now let's talk about reflections. With reflections, again, the pre-image and the image should be congruent. Just as a side note, we write congruent as this. So I could say triangle ABC is my pre-image. Triangle A prime, B prime, C prime is my image, the new one. And to say they're congruent, we write an equal sign. But in geometry, since we're talking about shapes instead of like numbers, we have a little squiggle on top. This symbol right here, an equal sign with a squiggle on top, means congruent. It means they're the same. All the lengths and angles have the same lengths and measures. Okay, so with a reflection, you have a line that goes through the middle. And when you reflect over that axis of symmetry there, the image and the pre-image should be the exact same distance from that line. So see how like the distance between C to the line and C prime to the line, it's the same distance. Same thing from the line to A prime and the line to A. And if it helps you, you could even like fold your piece of paper over. Like on this problem, I want to reflect this rectangle across the y-axis, which is this line right here, the y-axis. If I'm going to reflect across that line, if you had this on a piece of paper, you could literally fold it and kind of see where you're supposed to end up. Or you could also just kind of see how far each point is from the line and then go the opposite direction. For example, point A is 1, 2 units from the line. So instead, go the opposite direction, 1, 2 units. That's A prime. C is also 2 units, and at this point you could probably just count from A to B. So it's supposed to be 1, 2, 3, 4, 5, 6, a length of 6. And since the image is congruent to the pre-image, I know that this will also be a length of 1, 2, 3, 4, 5, 6. So that's B prime. And it's pretty easy now to figure out D prime, and there we go. So I reflected it across the y-axis. It's a mirror image across the y-axis. If I wanted to go instead across the x-axis, I would flip it down. Again, you could fold your paper, or I noticed that this is 1 unit from the x-axis. So if I go 1 unit in this direction, and there we go, it's up 1, 2, 3, 4. So 1, 2, 3, 4 units, just to make sure that the image is congruent to the pre-image. There we go. The only way this might get a little crazier is if you reflect it across a different kind of line, like the line y equals 3. This is a horizontal line. If we go up to the line where y is 1, 2, 3, that's right here. All of these points have a y value of 3. If I were to pick up this rectangle and flip it over that line, or if I were to take this paper and fold it across that line, I would actually just get the same rectangle, because point A is 2 units from the line. If I go 2 units this way, I land on C. So that's A prime, and C prime would be over here. And B prime would be down here if we flipped it, and D prime would be up here. So I actually just get the same rectangle on this one, because the axis of symmetry went right down the middle. One other crazy thing you might see is some diagonal lines. So what if I want to reflect across y equals negative x? Y equals x is this line, the diagonal line where the y and x values are the same. If you make it negative x, basically this is a line with a slope of -1 and a y-intercept of 0. So we'll start at 0, and slope of -1. So down 1, over 1, down 1, over 1, down 1, over 1. It's this diagonal line that goes right down the middle of these quadrants here. If I'm going to reflect across that, think about folding your paper. If I fold this side over, it's going to land in quadrant 3 here. It's going to go from quadrant 1 to quadrant 3. So this one's a little trickier to figure out, like exactly how far from the line it is to that point. So what I would do is kind of count the points. So like if I were to fold this, where might it land? Right now from the origin to point C, we go right 2 and up 1. And so if I were to fold it, it would be down 2 and left 1. Do you see how those would kind of line up across that line? So that's C prime. Usually once you get one point, you can figure out the rest. If I folded it, A would be somewhere over here. And I know that from C to A, it was 1, 2, 3, 4 units. So why don't we just count? 1, 2, 3, 4. There's A prime. Same thing from C to D. I know it's 1, 2, 3, 4, 5, 6. So just go down 1, 2, 3, 4, 5, 6. And there's D prime. And then we can get B prime just by creating the rectangle. And you may want to check it, like fold it and see that it actually does match up. Notice the points are going to kind of be similar. So like point A was 2, 1, 2, 3, 4, 5. Wait, 1, 2, 3, 4. Yeah, 5. So the point A was 2, 5. The point A prime was -5, -2. So they kind of match, but they just got flipped and made negative. Okay. In the next video, we'll talk about rotations, but one final thing that I wanted to mention is that you can represent all of this stuff with algebra. For example, if I had the point x, y, and I wanted to describe this transformation, we use a little arrow to be like, it transformed into. So this is like saying, take any generic point, x, y, on your original pre-image, and how do you get to the image? Well, in this particular problem, we went 2 units to the right, which means we took all the x values and we added 2. So the way I can say that is I took all the x values and added 2, because we went 2 units to the right. And we took the y values and we added 1, because it went 1 unit up. And so this is how you could represent that transformation as a function. You have an input of an x and a y value, and this is your rule for what you're going to do. Same thing for this first one, except it would just be x, y gets transformed to x plus 2 because we translated 2 units to the right. And the y value didn't change, so I would just leave y as it is. Or like on these transformations, some teachers are going to have you memorize these rules, and I don't think you need to. I think you can just figure them out. If you reflect across the y-axis, let's look at what happened to the points. The point A was at 2, 5, and it became -2, 5. Or let's try another one. The point B was at 8, 5, and it became -8, 5. So like what's happening from the image to the pre-image? You probably notice the y value stays the same, but the x value turned negative. So that's what we're going to write for our rule. You would take any generic point, x, y, and transform it by making the x value negative and leaving the y the same. Notice this was a reflection across the y-axis, but the x value changed. The opposite will be true if we reflect across the x-axis. See how like point C was at 2, 1, and it changed to 2, -1. Point B, or point D was at 8, 1, and it changed to 8, -1. So you'll notice here that the x value is staying the same and the y value is turning negative. So this rule would be xy transforms to, nope, x stayed the same. X stays the same, y becomes the negative version. And then for this last one, you may notice a connection between these points as well. Like we already mentioned, point A started at 2, 5, and it became -5, -2. Or point C was at 2, 1, and it became -1, -2. So what's happening here? On these, you're actually flipping the x and the y, and you're making them both negative. So to write out that rule, we would say the point xy becomes, first of all, I changed the x and the y. So it's now yx, because they flipped, and they're both negative. This will always be true for reflecting across that line, but again, you don't have to memorize that. You can always just play around with what your new points are and just kind of see.